Hello and welcome to the Thermal Cafe webinar, Thermal RC Modeling Using a Spreadsheet. Thermal Cafe is a brand new website powered by electronics cooling. It's a place where engineers can watch and learn about thermal management. In addition to webinars on thermal management topics, visitors can view relevant videos and a schedule of upcoming web events. Check us out today and stay tuned for more website content. This webinar is presented by Roger Stout, Research Scientist, Packaging Technology, Corporate R&D for ON Semiconductor. Roger is a charter employee of ON Semiconductor. He received his BSc in Mechanical Engineering at Arizona State University in 1977 and went on as a Hughes Fellow to earn his MSME at the California Institute of Technology. In his 35-year career, Roger has authored and co-authored 61 technical papers. He holds 6 patents and has been a registered professional mechanical engineer in Arizona since 1983. This webinar will be interactive. You'll be able to ask questions and we encourage you to participate. Take a look at the GoToWebinar navigation pane. If at any time you have a question, we ask you to fill out the type box and hit send. To make the screen minimize and maximize, click the arrow button. To raise your hand to ask a question or to report an issue, click the hand icon. Roger will present a topic for 45 minutes with a slideshow presentation and then a live Excel demo session, followed by a 15-minute question and answer session. Now Roger will begin the presentation.
Well, good morning, everyone. Thank you for tuning in. Some of you may have been here a few months ago when I talked about pretty much the same topic, thermal RC modeling, but what I wanted to do today was really give you an opportunity to see some of this stuff actually happen live using Excel. So what I want to do first is kind of whip through some PowerPoints just to set the stage for it, but most of the time this morning I want to spend actually doing Excel. The point here is to do thermal RC networks, and thermal RC networks are all predicated on having linear thermal systems, so I want to just share a couple of fundamental points behind that. And then what I'm going to do once we get into Excel is I'm going to show you how I can generate a Foster RC ladder network from a heating curve. In this case it would be an experimental curve that I got from test equipment in my lab. And in doing that, we'll get quite a few topics in Excel, things like array formulas, named variables, how to use the solver, using constraints on variables. In this particular case, whether we fix the time constants in the ladder or whether we let the solver find those. Also, I'll spend a little bit of time talking about matching square root of t transient response using RC networks. And the final Excel spreadsheet that I have, pretty much I'm just going to be talking my way through it, but that'll be how to compute temperature responses to multiple power steps. So that's the agenda for this morning. Thermal RC networks are all predicated on having linear systems. And a linear system means you've got changes in output variables that are proportional to changes in the input variables. In the thermal world, that means that we've got temperature changes that are proportional to heat inputs. The governing differential equations are linear in both space and time. And in the thermal world, these would be properties that are constant: thermal conductivity, convection to film coefficients, which play into thermal resistances. And further, we have heat capacity and density, which play into thermal capacitance. These things would all have to be constant to have a thermally linear or a linear thermal system. Now, before we go any further, let's quick do a poll question just to see if everybody's on board with me.
Okay, we have a poll question for the audience. Which of the following properties relate most directly to thermal resistance? A, conductivity and density, B, conductivity and film coefficients, C, film coefficients and heat capacity, or D, heat capacity and density? We'll give you a few seconds to answer. We have answers coming in. And the majority said B, conductivity and film coefficients, and that is the correct answer.
Oh, excellent. You're all paying attention. So what are the consequences of having a linear system? The most important consequence is that we can do what we call linear superposition. For linear superposition, we have solutions to simple cases which can be combined using linear combinations to create solutions for more complicated cases. It applies both spatially and temporally, space and time. And just to illustrate that, the basic response that we talk about in the thermal world is a transient step response where we have a fixed power level that we just apply at time 0, and then we measure some kind of a transient response curve. So you will have seen curves like this all over the place. Using this very fundamental idea of a step response, basically we can synthesize the response to any power inputs. For instance, we can do 2 steps of power where the power changes at time A from Q1 to Q2. Well, that would be the linear superposition of the red line here, which is Q1, followed subsequently by the blue line at time A, which is the difference between Q1 and Q2, and those add up to Q2. So the response of the system will be the red line superimposed with the blue line that starts with a time delay of A, and then when you add them up, you get this little black curve. You can do the same thing for 2 completely isolated pulses where you turn on Q1, at time A you turn off Q1, at time B you turn on Q2, at time C you turn off Q2. And so you have the linear superposition of this red line followed by the blue line, followed by the second red line, followed by the second blue line, and that results in this overall transient response. You can take any completely arbitrary waveform and break it up into small pulses, steps up, steps down. You choose the resolution that you want based on what kind of temperature accuracy you want. So let's quick do another poll question and see if we're still together.
Okay. Temperature response to an arbitrarily complicated power versus time stimulus can be approximated by step responses. Is this true or false? We have some answers coming in. And almost everybody said true, which is correct.
Oh, excellent. All right. Laplace transforms are what we use when we're dealing with these kinds of networks. Although this slide has a lot of information on it, the real point here is you convert resistances in the time domain into impedances, and they just map directly across a constant as a constant. Capacitances, on the other hand, turn into a 1 over SC, where C is the capacitance, S is the S-plane parameter in complex variables terms. The responses that we're interested in are exponential responses. The unit step has a Laplace transform of 1 over S, and an exponential response in time has a Laplace transform of 1 over S plus A. These become important to know because as we manipulate Laplace transforms, basically everything we're going to do will result in an exponential response. And the basic idea behind Laplace transforms is that you've analyzed your system and you think of everything in terms of the S-plane, where we have a system that's described by theta of S. You can apply a stimulus, which is a temperature, let's say, measured at this outside, or the stimulus that's applied is Q of S, the heat input. You can define the transfer function of the system, theta, as the ratio of the, let's say, the applied stimulus Q to the response T. And you could actually, put this in any number of different ways. You could solve for temperature, multiplying the Laplace transform of the system function by the stimulus, or you could even go the other way around. You could use temperature as a stimulus and have the inverse of the system function to compute the heat. It's all mathematical manipulation. You can use the same circuit analysis techniques you learned in electrical circuits class for combining a complicated system and digesting it down into its Laplace transform. So you replace R's with the Laplace transform, replace C's with 1 over SC, you do your normal parallel series additions, and you get this transfer function. And note the form here, which we saw in the Laplace transform exponential. These are the form of a constant divided by the time constant times S plus 1. And it's just a summation of terms in this particular kind of a ladder. This ladder we'll call a Foster ladder, where capacitors tie rung to rung rather than going to ground. The other kind of ladder or network that we could have, we would call a tower network. In this case, the capacitors don't tie to ground. We use the same analysis techniques basically, but unfortunately we end up with some more complicated Laplace transform. We have these kind of continued fraction things. And here we've got a ratio of two polynomials, but it's not readily factored into the time constants. In fact, if we have many more rungs in the ladder, it becomes quickly intractable. But they're just polynomials in S, and if you can find the roots for the polynomial, you can use partial fractions expansion to get the individual time constants, thus converting this ladder, which doesn't have grounded capacitors, basically into its equivalent, which would have had grounded capacitors, where each RC product is a time constant of the rungs. And just to compare two large ladders, the one on the left is a Foster ladder, where all the capacitors just go rung to rung, they don't go to ground. The Cower ladder on the right, the capacitors go to ground. And although this is a numerical example which won't mean anything to us in this context, the point is this Foster ladder and this Cower ladder have exactly the same transient response. The R's and C's aren't the same, but if you go through the system analysis, you'll find that they have exactly the same time constants and the same response as a function of time if you're looking at the junction node. Another question to quickly answer is, if every ladder that we analyze is comprised of R's and C's, what's the response at the shortest time? And I've just done the Taylor series expansion here to show that when you have a whole accumulation of rungs in a Foster network, what you end up with is a response time a step response function that is a proportional, it's constant proportionality times time. So these RC networks always fall off linearly with time when the time constant, or the time gets short enough meaning something lower than the shortest time constant in the system. But also notice that all the time constants in the system are involved. Even if we're at a very short time, every rung in the ladder contributes something. So before we jump into Excel, let's look at our third poll question, and then we'll get busy with.
Okay. Attendees, please answer the following question. The short time behavior of an RC network below shortest time constant is what function of time? Constant time or B, constant square root time? Give you a few seconds. And the majority said A, which is correct.
Okay, that's good. Now I'm going to switch my screen over here, and I'm going to go to Excel. And I believe everyone should now see an Excel spreadsheet. Now what I've done, I've preloaded this particular spreadsheet with two columns, columns A and B, time, and in this particular case it was a diode temperature reading. There's going to be some noise in the data, but what I'm going to do is let's start by creating a chart. So I'm going to say up here, insert a chart, scatter chart. In this case, I don't think I'll bother with putting points on the chart. So there's a chart, and then what I want to do is I want to select the data that's going to go in this chart. So I'm going to select columns A and B, and I think if I do it, there I've got that entire two columns of data. I'm going to say OK, and if it worked right, there's my chart. But we need to do a little bit of work on setting the axes, putting this chart in a plot. Make the chart a little bigger. So let's make this a logarithmic plot. We're going to say format this axis, and I'm going to tell it. You see, I've got a lot of switching noise below 100 microseconds. So I'm going to just make the chart start at 100 microseconds. I'm going to make it end at 300 because that was where my data ended. I want the axis to cross at 1 - 4. And then I want to add some major and minor grid lines. Add minor grid lines. And then let's also change the vertical axis to go from 0 to 1. And so there's my experimental data. Let me get rid of that chart label, move that thing over there. Let's see a little more. And then I'm going to look at my note here. What have I done? So I reformatted the axis, I rescaled it. Okay, now what I want to do is I want to create an exponential fit function that I'm going to use to try to fit to this curve. Now I've already set myself 2 cells, let's say a time constant of 1/10 of a second, and we know that our total amplitude here is something approaching 1, let's say 0.9. So we want an exponential curve that's going to look like roughly this amplitude with a time constant somewhere in the middle. So let me do that. Let me create a formula here that says take the amplitude, row locked, times 1 minus e to the minus time. I'm going to get the time from column A, and then I'm going to divide it by my time constant. I'm going to row lock that. It's an F4 I'm doing to do the row and column lock. Okay, oh, I forgot to set a parameter. Excel caught that for me. So there's my RC fit. Now if I double click the lower right corner, that automatically extends that formula down the column. So now if I select my chart, I can tell my chart pick up data from 2 columns. So look at that. Now I have an exponential fit, which doesn't look very good. I mean, you can already tell an exponential curve is not going to match this data very well. So let's see what I want to do. Let's try to quantify the error. So my note here says expand the chart to include the show that, yeah, it doesn't work too well. So we're going to add an error column. So the error is going to be my RC fit minus the actual data. Again, I'll double click here to extend that down the column. I'm going to make my chart expand to hold the error. And then let's reformat that error by right-click here and say Format Data Series, put it on a secondary axis. And then let's scale that secondary axis to go from minus 0.1 to plus 0.1. All right, you can see that my error, which is the green line now, centered around 0, goes pretty far below and then pretty far above. And I would like my red curve to fit the blue curve better if possible. To fit it better, well, we could play around with it. Maybe my time constant isn't in the right place. Maybe I need a smaller time constant. Well, that moves the red line to the left. Oh, one other thing we could do is to quantify the error. I think I should have done that too. Let's compute the root mean square error, which is the square root of the sum of the squares of all the numbers in this column. And I also want to divide it by the number of cells that are in that column. So we'll go over here. So now I'm going to divide my square root, the sum of the squares, by the number of points, and I'm going to divide by the number of points and then take the square root of the result. Control-Shift-Enter turns that into an array formula. Notice the squiggly braces that appeared when I did a Control-Shift-Enter. If you just do a Control-Enter, you don't get the squiggly braces. Or if you just do a regular enter, you don't get the squiggly braces. If you do a Control-Shift-Enter, you get squiggly braces. Also, I don't want to include the error below the, probably below 300 milliseconds, or maybe in milliseconds. What did I say here? Pick the time to 300. That was my note. So I want to go, instead of going to all the way down to time 0, or where my first experimental data came in, I'm going to go down to row 33, which is at 300 microseconds. So at row 33, I'm changing my formula. So now my total amount of error, or my root mean squared error, from 300 microseconds all the way out to 300 seconds is 0.093. And what happens if I start fiddling with my amplitude? Well, I drop my error from 0.093 to 0.08 by changing the amplitude a little bit. How about if I change the time constant a little bit? Oh, I got the error to go down a little bit more. So you can see I can make the error get smaller, but I'd really like to let Excel do this for me. So what I'm going to do is I'm going to open the solver. The solver comes in the data menu. You can see I have a solver here. If you don't have the solver in the data menu, then you need to go to your Files, Options, And under Files Options, there's Add-ins. And then when you go to Add-ins, down toward the bottom, you've got several choices of add-ins. You want the Excel add-ins. You say Go, and then you'll get this little pop-up that's got several things. I usually have my Analysis Tool Pack, my VBA Analysis Tool Pack, and my Solver add-ins. But the Solver is the key right here. If you don't have the checkbox on the Solver, you're not going to see the Solver on your data menu. But once you've activated it, will always be there. Excel will remember that every time you launch it until you go back in and tell it you don't want it anymore. So here we have the Solver. To launch the Solver, basically I tell it what cell do I want to use as my objective. In this case, it's my RMSE cell, which is E2. I want to minimize the error, and I want to do it by changing these two cells, the tau and the amplitude. I don't have to add any constraints here, but I do want to make sure that in this case the variables stay non-negative. Probably will avoid some issues. So I've got that set up. I just say solve in the lower left corner. That happened so fast we didn't see it. But basically Excel worked on those parameters, and it managed to get our RMSE down to 0.0748. And it did that by setting the time constant at 0.0417 and the amplitude at 0.82. So we were in the right ballpark just by using our eye, but the Excel solver has basically taken us all the way to the minimum error we could possibly get. Sometimes I run the solver a second time. Sometimes it stops a little earlier than you need it to if you restart it. On a second pass, it uses tighter tolerances or something. I'm not quite sure why it doesn't go all the way the first time. But anyway, that's as much as I want to show on this particular sheet. So I'm going to go to the Step 2 file. So let me just close this guy. Let's save the changes. And I have the second file, Step 2. Step 2 basically looks like where we were. So what I want to do is I want to show you how to add a rung to the model. To add a rung to the model, in this case, I'm going to go ahead and type in, just so we have some numbers to work with, 0.4, but I'm going to cut this back to 0.42 so that the two amplitudes still add up. So to do that, I have to take my RC model, and I could do a couple of things. You know, I could actually add in a second term, just like the first one, where I take the amplitude, multiply by 1 minus exponential of minus time, divided by my second time constant. I could do that and have basically a complete analogy to the one-rung model that I had before. But I can use the things that are called array formulas in Excel, especially if I'm going to be adding more rungs. This is going to become really tedious. So instead of doing it that way, let me use the sum function and say to Excel, look, I want you to sum up all these amplitudes times all these time constants. There I can grab that one. So I've extended my amplitude to 2 cells, my time constant to 2 cells, because they were row locked before. They continue to be row locked. But the sum function tells Excel, use this whole array, and if I do Control-Shift-Enter, it's going to add up. I did the same mistake, left off too many. Didn't have enough parens. When I do Control-Shift-Enter, it adds the squiggly braces, and basically it tells Excel that it's going to use both of those terms, sum them up, and just give me the result. Now I have to extend that formula down through the whole column. And when I do that, notice what's happened to my chart here. I don't know what that did to your view. I thought my chart was just a smidgen bigger than that. Okay, I hope you can still see the whole chart. Well, you can see that the error isn't a whole lot better, but I have 2 degrees of freedom to play with now. So what I want to do now is I want to rerun the solver. So let's go here, data, solver. It's remembering the target cell from before, but I do need to expand my the variable cells to include all 4 of those cells. Again, I'm not going to add any constraints. I'm going to make it sure that everything stays non-negative. I'm going to say solve. And let's see, this one said, okay, it ran a time constant to 0. So I'm going to fix that by adding a constraint in the solver. I'm going to tell it that I want my time constant cells to never get smaller than. I want to make sure that they're always bigger than. In this case, I'm going to say O2. Okay, so now I have a constraint that basically says no time constants can get down to 0. They're going to have to stay bigger than, in this case, 20 microseconds. And I'm going to rerun the solver, and I probably needed to reinitialize that to something bigger. Let's try one more time. Okay, in this case, the solver managed to converge to a solution, and you'll notice now that my error goes up and down twice. So I've got 2 lobes of error, and if you look at the red line, you see how the red line kind of waves above and below and above and below my blue line, which is my target function. Okay, now my note here says add another rung to the model by inserting a row in the middle, and observe how everything adjusts automatically. So I'm going to grab 3 cells. I'm going to do Control plus on my numeric keypad. It's going to ask me, do I want to shift down or to the right? So I'm going to say shift down. I'm going to insert a new numerical value in here for a time constant. Let's give that 0.1, and let's take off 0.1 from that rung so they still add up to what they added up to before. Now, clearly my fit isn't as good as it was. My error has gone up. But I now have a formula which has automatically adjusted itself because I inserted cells in the middle of the table, and my formula for my exponential function has already expanded to include that. Not only that, the solver has also tracked that change, and the solver has automatically adjusted to say, well, he wanted to change from rows 2 to 3 before, but he inserted a row. So it's already set up. It's changed my constraint. Everything is beautiful. The solver has noticed what I did and adjusted. So I'm going to solve again. It's going to go off and solve. Look at what's happened now. My curve is starting to fit the line even better. And I've got 3 lobes of error, and our error is ranging around, plus or minus 0.02 now. My root mean squared error has gone down to 0.015. So things are looking better. And you can kind of see how if I were to add more and more rungs, I could fit this curve closer and closer. Before I do that, or at least show you what the results are, let me show you about named functions. Because up till now, my RC model has been based on these cells, which, well, the formula is not terribly complicated, but it's not, it's not really friendly. So let me grab these cells here and go into my formulas menu and tell the name manager that I want to create some names. It gives me an option of going to create names from the values in the top row. Yeah, I made a good guess. So I'm going to say OK. And now if we go look at the name manager, you'll see that I have 2 names, a name called amplitude and a name called tau. It even tells me where on the sheet they refer to. So I now have some named variables. Now my formula still doesn't use those names, but if I go up to the name manager here and say define name, under that little menu there's an apply names. I can say apply all those names. And look at what it did. It took tau and amplitude, which it now knows, and it applied them to my formula. Not only that, it applied it to everywhere on the whole spreadsheet that it could find a place. So now my formula is a little bit more human friendly. It says amplitudes times 1 minus e to the minus time over tau. So I'm using names. Everything else would be just the same, and I can add more rungs by grabbing those 3 cells, doing another control plus, adding another cell, just like we did. Everything is going to adjust. The solver is going to adjust, and all that stuff. But instead of adding more rungs, I'm going to switch to another spreadsheet where I've already done it. I've gone up to 6 rungs, and let's do poll question 4 while I'm fiddling with the next sheet. You go to poll question 4. I hope the moderator is sharing. Hello?
Hello?
Whoops, sorry, Roger.
Hello?
Are you going to a poll?
Yes. Yes, we're going to poll question 4.
Great.
Sorry about that.
We didn't hear you, sorry. What special keystrokes are required to enter an array formula in Excel? Control-Delete, Alt-Shift F4, Control-Shift-Enter, or no special keystrokes are required. We'll give you a few seconds. And the Majority said C, Control-Shift-Enter, which is correct.
Okay, good. Now somehow I managed to close. Sorry, this wasn't supposed to happen. I seem to have closed the sheet that I wanted to have open. There we go. Let's try here, sheet 3. Okay. Now on this sheet, I've got the results of having gone up to 6 runs, and I put a chart here that shows how the root mean square error fell every time I added a run, which should be a good surprise here. In fact, we've cut the error by at least an order of magnitude by going from 1 run to 6 runs. And if I hide that or send that chart to the back. So here's the result after having done 6 runs. Notice that, I've still got 6 little waves in my function. But, to your eye, you can see that we have followed the blue line pretty darn closely with just 6 runs. Now notice how the error fell off. Remember I had originally set my root mean square to go from 300 microseconds out to 300 seconds. So it's kind of interesting that the error definitely falls off dramatically. And you might ask yourself, well, is this just experimental noise, or maybe, maybe I've got real data in there, but could I, in fact, turn that exponential curve fast enough to follow that data? Well, to follow that data, let's increase our RMSE function to go all the way back to 100 microseconds. Let's see. So I click here, and that's going to take us down to row 17, as I recall. And again, I'm going to do Control-Shift-Enter. Now my root mean squared error changed. It doubled from whatever it was, 03 something to 06. But let's rerun the solver and see what the solver says. See what the solver says it can do. So same cell, same variable cells, 2 through 7. And let's see, I don't have any constraints, so this probably got lost. So let me go back and add that constraint. That the taus are going to stay greater than or equal to 0.0002. And then let's solve. And when we do, well, look at that. See that curve just snapped right in there? Now we've got, you can see the waves a little bigger because we've traded off error. We made a better fit down here, but it was at the expense of the overall curve. So we might talk about adding more runs. Now that we know we can fit the curve better elsewhere, the only way we're going to be able to do that is by adding runs. So I can add 2 more runs by, in this case, I'm going to select 2 cells kind of in the middle here. Actually, I think what I did before. Notice there's a big time jump between this run and this run. Let's add 1 cell here. And there's another fairly big time jump. Well, I'm going to throw it in here and let's see what happens. Let's shift down. So I've made room for 2 more runs. Let's make this time constant 0.003 and give it a 0.05 and then take off 0.05 from there. And let's make this time constant 10 and we'll put in a 0.05 and take off 0.05 from that one. So again, I've definitely messed up my overall fit, but I want something that at least the solver has something to start with that hopefully it'll do a pretty good job with. So I'm going to, I'm trying to make my screen bigger. Sorry, but I'll leave that alone. Pick the solver again. Notice the solver has, again, it's adjusted. It already knows that we need to go all the way down to row 9, remembering the constraints. Oh, it even renamed the constraint to apply to tau. That's interesting. So let's say solve. Now down on this, that took long enough that if you were looking at the lower left corner, you might have actually seen something. Well, now look at what that fit is like. With an 8-run model, we got our error down all the way to 0.0039. I think I'll run it one more time. Let's just see what happens. And look at the lower left corner down here. There you can see it working. It's showing you the error as it makes it fit. And it spent quite a bit more time there. What happened to this time constant? Well, I think it just got too many digits. Yeah, so we've got a time constant out of 130 seconds now. But that still makes physical sense because our data, we've got data all the way out to 300 seconds. So Oh, I probably should have been, that might be what we're doing. Should have made my screen enlarged to fit my Excel window. But we've got a pretty darn good fit now. You can see you really don't even see any ripple. The rung-to-rung ripple is gone. What's left over now is the experimental noise. And when your experimental noise is that large compared to the fit of the RC ladder, basically there's not any point in trying to get better than that. It just doesn't make a whole lot of sense. So let's go to the next sheet, which is sheet number 4. If I did that right, it's already loaded in here. Sheet 4. Okay, so let's talk about the square root of t function for a minute. I've kept the experimental data from the previous model, and I have kept the RC model, the 8-rung model from the last sheet. And this model follows experimental data pretty much until it goes nuts due to the switching effects. I also changed my plot axes here, so I've got a log-log plot. So I changed my vertical axis to log scale instead of linear. And let's talk about these short time responses. We have, if I put a linear fit, like here's a linear fit where I've got 50 times time, that's what this column is, and plot that linear fit, notice this nice purple line which goes up 1 decade of response for every decade of time. On the other hand, I could do a square root of t function, which if you were doing surface heating models, for instance, square root of t is what the theory says the surface temperature should go up. So here's this green line is a square root of t. On a log-log plot, that square root of t line goes up 1 decade for every 2 decades to the right. So it's got a 1-to-2 slope instead of a 1-to-1 slope, which was the linear line. Well, what I want to do is show you another Excel trick that maybe you don't know. I can shift all my experimental data up or down very easily. Now, I've got raw data here. These are just numbers. What if I wanted to add a constant to all those numbers, or I should say a constant, an adjustable constant? So let me put a formula in the cell F1 that points to cell F2 right there. I'm going to do row lock. So I've got an equal to G1, which is row locked. So any number I put in here, like 0.1, is going to appear in cell F1, right? So you with me? I've got this formula, which is G1. What if I copy this formula and paste it to this column? But instead of doing a normal paste, I'm going to do a paste special, and I'm going to say formulas add. Now watch what happens. This is a cool trick. Notice what it did to every single formula in this column. It left the original number, but it added to it this fixed cell reference, G1. So now every single formula in column B points to cell G1, where I actually don't have a number yet. In fact, I don't even need the formula I just created in F1. That was just a sort of a temporary formula. G1 is the one that matters. If I put in a 0.1, watch what happens. My whole line just shifted up by 0.1 or minus 0.1. It shifts down. Notice what's happening to that line. I can make it move all over the place. Oops, sorry. So I might move it down by minus 0.01, minus 0.02. So I can make that line start to look like it has a 1-to-2 slope. If I move it down a little farther, I can make it look like it's got a 1-to-1 slope. Basically, it's an arbitrary decision on my part as to what my short time response is going to look like, especially because I've got experimental noise. So maybe I've got a theory that tells me I have square root of t heating. I really want my experimental data to look more like a square root of t curve at the shortest time where the data is probably good. But maybe I know I've got volumetric heating because my PN junction is deep enough, deep trenches or something. But I really do have volumetric heating in the time scale that I've got data. So maybe I need to make it look more like this. Now, my vertical placement of the purple curve, of course, is arbitrary. I mean, I could have put that purple line anywhere just by changing the multiplier. But if I'm looking at my experimental data, that doesn't make sense for a linear fit. 50 is probably better than 100. Similarly, for the square root of 2, I can change my square root of t parameter, and I can move that square root of t line anywhere I want on the chart. In this particular case, I had preloaded it to what I knew was going to be about, the right place. But these are the kind of games you play with experimental data when you don't actually know the starting temperatures. In my case, which I didn't describe, my experimental data came from a cooling curve, and I've got switching noise, and I've got switching time, and I don't really know what the temperature was at time 0, so I'm going to have to guess exactly where do I place the curve vertically. All right. Yeah, I think I've said everything about this page that I want to say, so let me go on to my next sheet, which is number 5. So we have this square root of t reference line, and the question is, can I fit an RC model, an exponential function model, so that it looks like square root of t? Because ultimately, if I'm building these Foster models or Tower models, I need to make them fit some experimental data. And besides fitting experimental data, I needed to match whatever I believe is the right theory at the shortest times where probably I couldn't make measurements. So let's start with this is 10 times square root of t. That's my function. I'm going to try to fit it. So I'm going to create a 7-rung model with my first tau at 100 milliseconds. So let me put in my, 100 microseconds. I want every rung to be a fixed ratio of the square root of 10 times the previous rung. So let's say square root of 10 times the previous rung, and I'm going to drag that down until I've got 7 rungs. So that takes me from 100 microseconds to 1/10 of a second. 7 rungs. And in this case, well, my total amplitude, well, what range? It's going to be over, several. Oh, what? Let me make it. Let's just make them all 1. So each one of these rungs is going to start out as a 1. Can I tell myself I'm going to do something else? So I'm going to create an RMSE, the square root of the sum of the squares. Now I didn't give myself an error column, did I? Well, I don't actually need an error column. I just need to take the difference between that column. Oh, that was a bad thing. Sorry, I forgot one step. I need to make my RC fit first, because I need a function there to line up with. So we're going to go, let's do one other thing. Let's create names. So formulas, create from the selection, top row. Now when I type in this formula, I'm going to go the sum of the amplitudes times 1 minus exponential minus time divided by tau. Since it already knows those, sorry, Control Shift Enter. There's my function. There's my RC fit. Make the chart include that. Well, that does not look like a very good fit, but we're going to do a root mean square, the sum, the square root of the sums of the squares of the difference between the fit here, which now ends at row 43, minus the same range here, which is cell, and then we'll do 2 control, well, then I have to divide by the number of cells, which is the count, and I'm just going to copy this in here, because this range is the count, and control shift, well, too many params. Okay, control shift enter. Fortunately, Excel figures out usually if I have 1 too many or 1 too few. So there's my root mean squared error. Now I said I want to adjust the root mean squared error to go from 1/10 of a second to 0.1 seconds, but that's how long my data table was. So I'm already set there. And I think I'm ready to run the solver. So I'm going to say data, solver, there's my RMSEs in cell E2, minimum by changing just the amplitudes. I don't want to change the time constants here. I'm going to keep those fixed and just give fewer degrees of freedom to Excel to change the time constants. So I'm not going to have any constraints. Let's just see what happens. Well, that's what it was able to do. Did not do a very good job. So let's try to help it here by giving it some more numbers here, and maybe make that like 4. Let's try that. So my initial guess wasn't very good, apparently. Try again. Oh, crud. Let's see here. Fix the cows, find this, where's my note? Shift times. So let me just double check my from a millisecond. Ah, that's my problem. I went all the way out to a second, and I only meant to go to a tenth of a second. So let me change. I gotta get this where I can see it. So my root mean squared error is going to end at cell 33. So I'm going to go to 33 instead of 43. 33, 33, and 33. Control Shift Enter. And we're going to put these at 0.2 again. And make that there. Try to run the solver one more time. Please work. Oh, that looks a little better. Oh, much better, in fact. Look at how well that fits from 100 microseconds out to a tenth of a second. Let's run the solver one more time and just see if it wants to narrow in any better. Not particularly. And also notice that it still decided it didn't need this run at 30 milliseconds. But it's a darn good fit. Let's see if my notes tell me anything else. Let's see, create a linear reference line. I did that. Start. The sum. Let's see. Did I? Whoop. Oh, okay. I want to shift my starting time in the plot to a microsecond. Let's look at this first. Let's go from a microsecond out to 0.1 seconds. And when I do that, let's also adjust the vertical axis to go from 0.01 to 1. And the reason I did that was the square root of t. Oh, and now I'm going to change, because of the way I set up my table, I can also make this table start at a microsecond. So I haven't changed my curve. I just extended it to shorter times. And so here you can see how the square root of t falls off, and it becomes very inaccurate compared to the square root of t. The square root of t is the blue line. The RC model, because I had given it a shortest time constant of 100 microseconds, once we're below 100 microseconds, it falls off linearly with time instead of following the square root of t. So one question you might ask yourself is, what was the slope of this square root of t function? So let's add a constant here, the 50 row lock times the time. And let's extend that down, and then let's make our chart pick up that linear reference line. So there's a linear reference line. Where do you suppose we have to put that? 200, 800, 1,000. 1,000's getting pretty close. Maybe 1,300. 1,300 looks pretty close. Well, you remember how I showed you the short time response was the sum of the amplitudes divided by taus of all the rungs. What if we do that? What if we say, what's the sum of the amplitudes divided by the taus? It's 1,315. What that tells us is 1,315 actually is the perfect fit for that curve. Let's go one more decade. Yeah, so you can see that we could have predicted exactly what the short time response of that RC model was by computing the sum of the amplitudes over the taus. And sure enough, that's right. Okay, I'm ready to go to the last sheet. I think I have one poll question 5. So if the moderators are paying attention, let's do poll question 5.
Thanks, Roger. How many rungs per decade does it take to make an RC ladder fit a square root time function? 1 rung per decade, 2 per decade, 7 per decade, or you can't fit an RC ladder into a square root t function. We'll give you a few seconds to answer. And we have a bit of spread of A, B, and C. Back to you, Roger.
Okay, well, I'll just comment on that because the one rung per decade might actually work. Oops, I'm getting some kind of an error here. Okay, I hope everybody can see this. The one rung per model might be good for some situations. 2 rungs per model per decade is what we just did on that fit, and you can see that that fit was pretty darn good at 2 rungs per decade. 7 rungs per decade, I would say, is really overkill. And as for you can't do it, well, I would say, well, I don't know if anybody answered you can't do it. Obviously, you can do it. We just did it. And so I would say, kind of rule of thumb, anywhere between 1 and 2 rungs per decade is good. It just depends on how accurate you want to be. If you do 2 rungs per decade, you're well within 1%, more like 2 or 0.3%. Okay, the last thing that I want to do is just talk about how you implement multiple pulses. Don't really have time to build the spreadsheet for you, but I've got it built, so let me talk about it. This is what we're trying to do. Notice the red line here, if I make that a thicker line just so we can see it, this is my power input function. It's a complicated, high power shifts to medium power, low power, then it goes back up. The widths are kind of random, the heights are kind of random. That's the power function that I want to stimulate it. And what I have is an RC model. In fact, I think it was the RC model, the 8-rung model that I just did in the previous demonstration here. What I want to do is I want to compute the temperature response. So that would be undoing my thick red line, sorry. And I want to do the blue line, and I want to make it, I want my temperature responses of the blue line to respond to the red line. So I have to build a spreadsheet that can somehow accumulate all those individual pulses. So we turn one on, and then we change the power, and we track that for a while, and we change the power again and track that for a while. Basically, that's what this spreadsheet is set up to do. So we've got the RC model here with my taus and my amplitudes. In row 18, I've got a list of times, and these times are the times at which the power changes. Or in this particular case, I've thrown in a few extra times besides, just for simplicity. In this case, I'm going to build a column a little bit later on. I'm going to use this transpose function, and I'm going to actually get my times in this table down here by a transpose of those times. Don't have to do it that way, but in this particular case, that was how I did it. Point is, on row 18, as the minimum, you have to have the times at which the power changes. Row 19 are the power changes, or I should say the applied power. So I'm applying 233 watts all the way out to 23 milliseconds, and then I drop from 233 down to 100. And then at 58 milliseconds, I drop down to 10. At 87 milliseconds, I go back up to 42. I hold 42 for quite a while. Those wouldn't necessarily have to be in the table here unless in this case, I wanted to see what the temperature response was at intermediate times. They don't have to be in this row, they just have to show up down here later. But I put them in both places for convenience. Okay, row 20, basically I'm computing the delta in power at each time. So the power starts out at 233, but it changes by 0 to go from this 233 to this 233. And again, the change is 0, the change is 0. Now the change is a minus 133. Here it changes to another minus 90. Now it goes plus 32. So if you remember from how I synthesized the more complicated multiple pulse function in the PowerPoint slides earlier, this is how I'm doing it in Excel. I'm computing each one of these columns basically represents the beginning of a new pulse. Now, of course, if the pulse has got a power of 0, it's not going to contribute anything. But anytime that pulse has a non-zero contribution, we're going to start to accumulate the result. In cell A22, this is a key cell in this analysis, because basically what I have to do is I want to say at some actual time, let's say 1/10 of a second, how many of these pulses have already been turned on. So row 22 is basically telling me how far after this particular pulse nominally began have we progressed. So as long as we're 0.1 seconds, notice 0.1 seconds says that each one of these preceding pulses has been on for longer and longer and longer and longer, whereas pulses that start after 1/10 of a second haven't even turned on yet. So that's the purpose of this formula. It says if the difference between this time and my time of interest is greater than 0, then compute that time difference. Otherwise, put a 0 here. Because if I put a 0 here, I'm not going to get any contribution. In row 23, so here what we're actually going to do is use that RC model. So that should look like a familiar function by now. It's the amplitudes times 1 minus e to the minus t over tau. And I'm using the sum function, and I am multiplying it by the power of that individual pulse. So each cell here in row 23 is the cumulative effect of this particular pulse that's been on for this long. So here's the response of this pulse that's been on for only 40 milliseconds. This pulse has been on for 13 milliseconds. This pulse hasn't been on at all yet, so it has no contribution. So each one of these cells in row 23 is an individual partial pulse, and then my sum of all those pulses right here, that's the sum of everything in row 23 plus ambient, that becomes the total response of all pulses out to time 1. In the table then, this is the last piece of this spreadsheet, basically I used the Excel table function to create a table. And so to create that table, I selected the whole range of the table, which was like so, and then I went into my data menu, and in my data menu I said, what if analysis data table. And I'm telling it that I want every row in this table, sorry, every column, this is a confusing part of Excel with terminology. The column input for my time is going to come from cell A22. And by definition, it gets the result by applying that time to the formula that's at the top of the column. So this table, which I have just built, is basically now giving me the transient response of this complicated wave function, or waveform. And that's what I plotted. So that's the blue line. So that's everything that I've got to show you today. We should still have a few minutes left. Oh, Alice ran out. Sorry. Did that again. If you got questions, I guess we got a couple of minutes.
Thanks, Roger. We'd like to have a call for final questions. We just have a few minutes left. Please enter any last questions you may have in the navigation pane. Roger, here's a question for you. Why can't you work with Cauer networks in Excel?
Well, the big problem with Cauer networks is because you have to factor that that polynomial. The denominator of the transfer function when you went through the Cauer circuit analysis gave you a big polynomial, and there's, I guess, mathematical theorems that show that once you're over 5 runs, there are no closed form solutions, and that means you need to solve the roots of a polynomial, which you can't do with simple features in Excel. I've tried. One of these days I'll write myself a Visual Basic program to try to do a root finder. You can probably buy a third party, but to me that kind of defeats the purpose of using Excel. If you can't just use the built-in features. But anyway, that's the problem. A Cauer network requires that you factor the roots of an nth order polynomial.
Okay. How do you control the short time response of an RC network model?
Well, as we saw in this demonstration here, you can make the RC model fit a square root of t. You just have to pick the time constants. Once the time that you're trying to match falls below the shortest time constant of your RC model, you will not be able to do square root of t. But square root of t isn't necessarily what you need. You might have a physical model that shows that the linear roll-off in time is right, in which case it's a matter of choosing the right time constant and let your RC model actually do what you want it to do. But it's a choice, it's trading off time constants, and the summation of the t of the amplitudes over the tau is for the runs of the model to get the short time response, what you want.
One last question. How many rungs does it take to accurately represent a transient thermal response curve?
The rule of thumb that I use is one rung per decade. And I think pretty much what I showed you today, fit in with that. We went from 100 microseconds out to 300 seconds, so that's 7 orders of magnitude, and we had a really good fit with 8 rungs. So that's my rule of thumb: 1 rung per decade. If you've got really clean experimental data, you could do more rungs per decade than that. My data never justifies it. I'm easily within about 1% with 1 rung per decade.
Great. We have received so many great questions we will try to address in the future. Roger, thank you again for your time and expertise. Attendees, if you have any more questions we didn't answer here, please send us an email at info@electronics-cooling.com. A recording of this webinar will be available on our website, www.thermalcafe.com. We will also send a link to all participants shortly. Thank you for attending.
Thank you all.